Okay, Assalamualaikum and good day. So we're going to continue. Okay, wait. What is this? Cancel. This one, just put it away. Okay. So we're going to continue after learning on the clamper circuits. Okay. Now we are going to learn about the another types. Okay. We going to specific to one type of diode, which is called ZENER diode. So without further ado, let me go to the slides of ZENER diodes. Okay. So we're going to only cover part one of the ZENER diode, and I'm going to either record or face-to-face, depends on the second parts of the ZENER diode. So we're not going to cover all ZENER diode in these recordings. Okay. So today we're going to learn about these special types of diodes called ZENER diode. So ZENER diode Z. So you're going to have a diode just like a normal diode. However, you're going to have it's a ZENER diode. So you're going to have a circuit with a symbol like a Z here. So this is what we call as a ZENER diodes. Okay. So we're going to learn about these IV characteristics in the data sheets. Okay, so this is the part one of the diodes that we're going to cover. Okay, this parts will be later on. Okay, we will not cover it in this video. Okay, next. So regular diodes and ZENER diodes. Okay, so ZENER diode is designed, okay, to specially operates, okay, operation of ZENER diodes. Why we want to use the ZENER diode? Because the ZENER diode, the special function is to operate in the breakdown regions. If it's operate in forward bias, it is just like any other diodes. Okay, nothing special, just like another general diode in terms of forward bias. But we will going to have specific usage of ZENER diodes if it's actually being used for the reverse breakdown regions. Okay, so the IV characteristic of a regular diode is separated into three regions. One is which is the forward bias. So at this stage, current is being conducted by the diodes. Second, reverse bias, where the current is actually effectively blocked, okay, or very small current, very small is being flowed, as if there is no current, like a block of current for ideal diodes. Okay. Next, breakdown regions, okay, where the diodes is potentially will be overheat and damage. Okay, so regular diodes in this red font is manufactured to work well in the forward region. This one is for the regular diode. However, ZENER diode is different because it manufactured to work in breakdown region. So this is speciality of our friend ZENER diodes. Okay, so this is your ZENER diodes. This is the packaging. Okay, the physical outlook. So this is your ZENER diodes, and this is the symbol of it. Okay, so this one is look like Z, so ZENER diodes. So because it is operate in a breakdown region, okay, so for VZ, okay, not VD, not voltage drop or diode drop, is VZ, which is ZENER voltage, because it's designed to operate in breakdown region. So this one, opposite polarity for the VZ. Okay, so IZ, okay, is being opposite directions of the normal diodes, okay, for ZENER diode, because ZENER diode is designed to operate in breakdown region. So opposite polarity. So this is IZ, ZENER current. Okay. So this for still maintain for anode and cathode, okay, referring to the general diodes, okay? But because we must take account the Zener diode is operate for breakdown regions, so that's why we have this positive negative, which is opposite polarity of the because it's designed for breakdown region, and IZ is opposite. Okay, IZ Zener diode, Zener voltage, not diode voltage, diode current. That is different. That one is forward bias. Okay, Zener diode designed to operate in the reverse breakdown, mainly used for voltage regulation. Okay, mainly so if the question asks what is the use for Zener diode, okay, so one of it is voltage regulation for your maintaining the voltage and for limiting of application. In reverse bias, the Zener diode is on, okay, because it's specifically designed to operate in breakdown region, and the voltage across the Zener diode is called Zener voltage, which is your VZ just now. Okay, in forward bias, Zener diode act like the regular diode, nothing special. Means in forward bias, if it's ideal, it's like short circuit. If it's practical model, it's like a diode drop. For example, if it's silicon, 0.7, 0.3 if it's germanium. Note that the directions of the current flow is different between Zener and regular diodes. Okay, so if we were to see from slides, okay, so this is your IZ, opposite direction. If we are using the diode, the regular diode, it will be using this ID, because the regular diode is designed to operate in forward bias region. However, Zener diode is designed to operate in breakdown region, which is in the reverse bias. Okay, that's why it's different, the directions. Okay, so Zener diodes IV characteristic, VI characteristic. Okay, so black circle regular diode operating region. In the forward bias regions, the diode or the Zener diode is operated just like any regular diode. So if this is germaniums, using germanium semiconductor, it will have VT 0.3, and if it's silicon, it's 0.7, and so on. However, Zener diode, because it is designed to operate in breakdown regions, so we are more interested in the reverse bias of the Zener diode, because the nature was intended for breakdown regions. The red circle is the Zener diode operating regions. You see here, Zener diode, because breakdown region. If it's in the normal regions, we call it like regular diodes. So if you can see for the germanium, okay, the germanium, this is your VZ with Zener voltage, and this one is VZ for your silicon. So you can take note, the VZCI is actually more negative than VZ, just like in the forward bias. So the VZ, VD 0.7 silicon is more positive than VD 0.3 germanium. Okay. Zener diode IV characteristics. So you have this IZZK, which is actually denoted for Zener knee current, where the, as you know, where we learn the knee is actually the starting point where the current increase rapidly. Then we have Zener T is Zener test current, okay, which is what is the value of the Zener voltage at a given Zener current, Zener test current. And then we have IZM, which is actually the Zener maximum current. Okay, so what is the maximum current that can be flowed through your Zener diode? So this one is taken from the Thomas Floyd. Okay, so you can refer to that reference book as well. So the IR must be large enough to put it into breakdown. Okay, otherwise it will not go to breakdown regions. Okay, it's just in the reverse bias region, because we want the Zener diode to enter breakdown region. Breakdown effects begin at the knee point, okay, which is this, where the current start to increase rapidly. to put the zener diode into breakdown region, Iz must be equal than Izk. So for it to be in reverse in breakdown regions, so it must be greater than Izk. So which is here, okay, greater. If Iz less than Izk, the zener diode acts just like a regular diode off, which is open circuit if it's a practical diode. So if it's here, okay, so it just like act like a regular diode. Okay, zener diode maintains a nearly constant voltage across its terminal for value of IR ranging from Izk to Izm. So from here until Izm, it's maintained nearly constant voltage values, which is easy, right, in terms of your x-axis. Okay, means nearly constant voltage, not constant. If constant macam 10 volt, 10 volt, 10 volt saja, which is not true. But nearly constant means, for example, 10, 10.1, 10.2, something like that. Still not really like simply 10, 12, 13, tak. Okay, so it's nearly constant voltage. So it's very little of delta V difference. Okay. So, okay. Izk minimum value of IR to keep the diode in breakdown. Izt test current, where this value nominal VZT specified on the datasheet. We can see this in the datasheet. Izm is maximum current, above which the diode may be damaged due to excessive PD. PD is power, okay? So above Izm, the diode will be potentially damaged. Okay, so that's why we have Izm, maximum current that can flows. Okay, for the ideal diodes, and the practical diode model for the Zener diodes. For the ideal diodes, okay, so it is in terms of because it's operate in breakdown regions, okay, because it's operate in breakdown regions, so it's a reverse bias for the Zener diode. So when in the ideal model, so this is your positive and negative Zener voltage. Okay, please take note because it's operate in breakdown region, so that's why we have opposite polarity than the regular diode. If it's regular diode, this one is positive negative, which is the VD. But for VZ Zener voltage, because breakdown region, so this one is opposite polarity. The next is the practical model. Practical model, if we have a sum impedance. Okay, we have impedance of the Zener impedance. Okay, so to take down for the VZ is actually for the practical model is actually the VZ of the Zener voltage. Okay, plus with the impedance. Okay, Zener impedance. So we see from the characteristics curve. Okay, so how we derive that ZZ is actually delta VZ over delta IZ, okay, which will come into giving value of your impedance. Okay, so delta VZ is here divided by delta IZ, which is this value. So we get the impedance, Zener impedance. Okay, the constant voltage is represented by DC voltage source. So next is the temperature coefficients. So coefficient means pemala. Okay, we have not pemala means value lah. Okay, DC temperature constant, if you see percentage over degree Celsius, specify the percent change. Okay, percent change in Zener voltage for each degree centigrade. Okay, so it's not in measure in centigrade. Change in temperature. So delta VZ, changes of Zener voltage, equals to VZ Zener voltage times temperature coefficient and changes in temperature, delta T. So a positive TC, which is this one, means that VZ is increases, okay, with an increase in temperature. So what if you have negative? So it is conversely lah. Okay? VZ decrease with an increase in temperature. Next. This is the example, and 0.2 volt Zener diode has a positive temperature coefficient of 0.05% degrees Celsius. What is Vz at 60 degrees Celsius? Start. Oh, solutions. So delta V is equal to Vz times Tc times delta T. So here Vz, Vz is Zener voltage, which is 8.2. Then Tc is 0.05% because this one is in percent value. So that's why 0.05 divide 100. 0.05 divide 100. So that's why you have another extra 2 here, zeros, because it's percent. Okay. Then changes in temperature, which is 60 minus 25. This one is room temperature. So you get delta Vz is 144 megavolts. Okay. Therefore, at 60 degrees Celsius, what is your Vz? Vz is 8.34 volts. Okay, which is the initial 8.2 plus if your delta V. So this is your delta Vz. Okay. Next is power dissipations. Okay. So Zener diodes. Okay. PD is equals to Vz Iz. So this is one of the equation for power, right? So PD equals to Vz times Iz. Zener diodes are specified to operate at a maximum power. So the maximum DC power. Okay, you see maximum DC power dissipation, which is your PD max. Okay, so this is maximum power. Above that, the diode will be potentially will be damaged lah. Okay. So Zener diodes, the data sheet, you must be able to know the data sheet. So you can actually Google the data sheet. This one have a more complete information. This one is just for the sake of the slides, so we don't show all values. Okay. So partial data sheet means not the complete data sheet for the 1N4728 and 4764. Series means you have multiple diodes under that same series. Okay, so you have this one, you have 14728 diodes series until 1764 means diode 1, diode type 1, diode type 2. So you have many diode models under this data sheet. Okay, 1 watt Zener diode. So IR for value is actually reverse for VR less than VNE. Means need to be more because it's operate in reverse breakdown, right? In the breakdown region in reverse way. So DORR must be less than VNE in order for it to start operate in the breakdown region. Okay. So if you see here, we have this nominal Zener voltage Vz at Izt. So test Zener current just now, and this is tested at this value Izt. So Vz at Izt, so Vz is 3.3 volt at 76 milliampere of Izt. Then this is maximum Zener impedance. ZZT at Izt is the impedance, is 10 ohm. At IZK, it is 400 ohm. And at IZK milliampere for the current is 1 milliampere. Okay, so this is IZK for this IZK. Sometimes manufacturer will give IZ max rather than PD max, but it's okay because it will you still can able to calculate P max is equal to IZ max time Z. Okay, so this is the maximum ratings of the data sheets of the Zener diodes for these models. The symbol PD is for the maximum dissipation or they able to be tolerated by the Zener voltage. So is DC power dissipation at ambient temperature 50 degrees Celsius. Operating and storage junction temperature range. So this one is temperature ranges So this one is at the junction of the, because you know diode is we have junction, right, semiconductor, and this is STG for the storage junction and temperature range. So it is from -65 until 200 degrees Celsius for it to operate. Okay, means it cannot operate below the -65 and it cannot operate beyond 200 degrees Celsius. Okay, so with that we're going to stop for this part 1 of the Zener diode, and we're going to continue in the next class. With that, Assalamualaikum and good day. Thank you for listening.